Knowing the mechanical properties of a material is extremely important when it comes to the safety and performance of applied materials. For example, don't you feel safer knowing that the bridge you cross every morning on your way to work can actually hold you up? Isn't it nice to get on a plane knowing that fatigue in the wings, fuselage, and engines was accounted for? The objective of this lab was to demonstrate the mechanical properties of several different samples of steel alloys through a tensile test. 2 of these samples were 1018 steel and 2 others were 1045 steel. To obtain the engineering stress and engineering strain graph, we connected a computer to the tensile testing machine. The equipment we used in the lab is as follows: 2 samples of 1018 steel, 2 samples of 1045 steel, a caliper, red marker, Instron 4411 universal testing system, extensometer, computer with graphing capabilities. Samples used for tensile testing typically exist in a dog bone configuration as shown. These samples are manufactured to certain length and diameter specifications. In this particular lab, the 1018 and 1045 samples were pre-thinned. This was done so as to obtain a smoother stress versus strain curve. The experiment began by first taking the dimensions of each sample using the caliper. This includes the diameter of the narrow bar section, the gauge length, and the radius of the wider ends of the sample. After these measurements, the narrow bar section is marked with 2 vertical lines, and the distance between the lines is measured with a caliper. These lines are later used for measurements as to the distance displaced between the pre-tested and the post-tested sample. The machine used in this lab is the Instron 4411 Series 9. It is a standard electromechanical testing system. The testing system consists of several components: a crosshead, load cell, grips, extensometer, and control panel. The specimen is set between upper and lower grips, and then the extensometer with rubber bands next to the specimen is set as well. For this particular video, an example of the tensile testing of one 1018 sample is portrayed. After the sample has been readied for testing in the Instron machine, the initial diameter of the sample is entered into a computer, and the extension rate of 1 mm per minute is set. As the load is applied, the data is collected and automatically sent to a computer so that the progress of the load versus elongation curve can be observed in real time on a monitor. The load is applied to failure. During the test, necking gradually occurs and the narrow section of the sample gets thinner and thinner. When failure happens, a noise accompanies the fracture and the sample breaks into 2 pieces. The computer monitor shows the fracture point on the load elongation curve. After fracture, the curve slopes down to 0. After the sample has fractured, it is removed from the grips of the Instron machine, and the broken pieces are held together so that the distance between the initial red gauge marks can be measured for final elongation. The neck diameter is also measured. The load and elongation data is downloadable. With the proper software, this data can be used to plot a stress versus strain curve for further analysis. From pre- and post-test measurements, calculations as to the engineering and true stress and strain can be made. Using the data from the test session, true stress versus true strain and engineering stress versus engineering strain plots can be made. But what are stress and strain? Engineering stress is the applied load divided by the original cross-sectional area of the specimen. True stress is the load divided by the actual cross-sectional area of the specimen at a certain load. Engineering strain is the amount the material deforms per unit length in the tensile test. And true strain is related to the current length during the test divided by the original length. From these curves, the elastic or Young's modulus can be found by determining the slope of the initial linear region, known as the elastic region. The yield point is where the material starts to deform plastically, which is where the curve is no longer linear. The ultimate tensile strength occurs at the peak of the plastic region. Necking occurs beyond the ultimate tensile strength, where the load starts to decrease. Overall, experiments such as the tensile tests performed here are important for determining material properties. Without information about these properties, we'd live in a much more hazardous world.